Welcome to another deep dive. Today we're going to be exploring black holes
Ooh,
and quantum information.
sounds pretty intense.
Yeah, it's a combo that sounds like a sci-fi movie, but trust me, this is some serious cutting-edge physics that's pushing the boundaries of what we know about the universe.
Yeah, it definitely has that mind-bending quality to it, and it all starts with these fascinating
And
objects.
the black holes.
Yeah, exactly.
I mean, I know they have something to do with the gravity, but
Yeah.
can you give me a breakdown?
Okay, so picture this, a region of space-time where gravity is so incredibly strong that absolutely nothing,
Nothing.
not even light,
Wow.
can escape. That's essentially what a black hole is.
So it's like taking something as massive as our sun and compressing it down to the size of a city.
Exactly.
Oh, wow.
And at the very center of this incredibly dense object, you have something called a singularity.
Singularity. That sounds ominous.
It is. It's where our current understanding of physics completely breaks down. Imagine a point with infinite density.
Oh.
And then there's the event horizon, the boundary around the black hole, the point of no return. Anything crossing that line is destined to be swallowed by the black hole's immense gravity.
That's both terrifying and awe-inspiring. It's like falling off a cosmic cliff with no way to climb back up. But we're not just talking about black holes today, right? We're also diving into the realm of
Quantum information.
quantum information.
Yes.
I've heard the term before,
Yeah.
but I'm not quite sure I grasped it.
So imagine two particles that are linked in such a way that their properties are connected no matter how far apart they are. This connection, this entanglement, allows us to know the state of one particle instantly by measuring the state of its entangled partner.
Wait, so are you saying that information can travel between these particles faster than the speed of light?
That's the intriguing part. The information transfer seems instantaneous, which brings us to a historical point of contention. Albert Einstein, along with Boris Podolsky and Nathan Rosen,
Tricky.
famously questioned this idea of spooky action at a distance in a 1935 paper. This became known as the EPR paradox,
Oh,
where they argued that quantum mechanics might be incomplete and suggested the possibility of hidden variables that predetermine the state of entangled particles.
so they were basically saying, come on, there's got to be a more logical explanation for this.
Exactly. They couldn't accept that entanglement could defy the locality principle,
Right.
which states that an object can only be influenced by its immediate surroundings. But then came John Bell
Oh,
and his
wow.
groundbreaking work on Bell's theorem in 1964.
I'm sensing a butt coming.
Uh-huh.
Yeah.
Well, Bell figured out a way to experimentally test whether entanglement was real or just a quirky theoretical idea.
Okay.
He proposed a set of inequalities that could be measured. If the measurements agreed with the inequalities, it would support the idea of hidden variables.
Okay.
However, if they violated the inequalities,
Right.
it would provide strong evidence for the validity of
Quantum entanglement.
quantum entanglement.
Gotcha.
Exactly.
So someone actually put this theory to the test.
In the 1980s, a physicist named Elaine Aspect conducted a series of experiments using entangled photons.
So they were testing the very fabric of reality with light. That's incredible.
Yeah, particles of light.
What did they find?
Aspect's experiments were nothing short of revolutionary. His findings showed a strong correlation between the entangled photons that couldn't be explained by classical physics, violating Bell's inequality.
Ah,
This provided solid evidence for the reality of quantum entanglement.
wow. So Einstein's skepticism about spooky action at a distance was actually proven wrong.
You could say that, and this opened up an entirely new world of quantum possibilities.
Right.
But when we start thinking about black holes and entanglement, it raises even more questions.
Yeah.
What happens when one of these entangled particles falls into a black hole?
Yeah, that's what I was just thinking. We've got this idea of information being linked
Right.
between particles. But black holes are notorious for their ability to gobble up anything
Yeah.
that gets too close. So where does that leave the entangled information?
And that's where we encounter the black hole information paradox.
Ooh. I knew there had to be a paradox somewhere in all of this. What is the information paradox?
Well, according to classical general relativity, anything that crosses the event horizon of a black hole is gone forever. It's information, every single bit of it vanishes.
Right.
But quantum mechanics states that information cannot be destroyed. It might be transformed or scrambled, but it can't simply disappear.
Right.
So what happens to the information of an entangled particle that gets swallowed by a black hole? This is the core of the paradox.
So it's like having two sides of a coin. One side says information is gone, the other side says information must remain.
Yeah.
How do physicists try to reconcile these two seemingly contradictory ideas.
There have been a number of proposed solutions. Stephen Hawking, for example, proposed that black holes aren't entirely black.
No.
They slowly evaporate over vast periods, emitting something called Hawking radiation. But this radiation didn't seem to carry specific information about what fell into the black hole, which didn't entirely solve the paradox.
So where does that leave us? Are we still completely in the dark about what happens to information in black holes?
Not entirely. There have been some very intriguing theories proposed. One of them involves the concept of entanglement entropy, which is basically a way to measure the amount of entanglement between two systems.
So we're not just talking about entanglement as a yes or no thing, but as something that can be quantified.
Exactly.
Tell me more about this entanglement entropy.
Don Page, a physicist who collaborated with Stephen Hawking, proposed that the emitted Hawking radiation is actually entangled with the black hole itself. This implies that information might escape in a scrambled or encrypted form. By calculating the entanglement entropy, Page found that as a black hole evaporates, the entanglement entropy first increases and then decreases, eventually reaching zero when the black hole completely disappears.
So the information isn't necessarily destroyed, it's just hidden within the entanglement between the black hole and its radiation. But how would we ever decode this information?
That's a question that continues to puzzle physicists.
Right.
And there are other theories out there too. For instance, physicist Leonard Susskind proposed that entanglement might act like a wormhole.
Wormholes. Now we're talking science fiction, right? But seriously, how could wormholes play a role in the information paradox?
A theoretical tunnel through space-time.
Okay.
Suskind's idea is that information could escape from a black hole's interior through these entanglement wormholes, preserving the principle of unitarity, where information cannot be lost.
So instead of being destroyed, the information takes a detour through a cosmic shortcut.
Yeah.
I have to admit, this is getting a little mind-bending.
It definitely challenges our conventional understanding of space-time and information.
Yeah.
But even if information escapes through entanglement or wormholes, there's still the issue of the timescale. The information might not be released until the black hole fully evaporates, which could take an incomprehensible amount of time.
So it's like sending a message in a bottle that's thrown into a vast cosmic ocean. It might reach shore eventually.
Exactly.
But it could take billions, maybe even trillions of years.
Exactly.
But there's another idea you mentioned earlier, a new thought experiment.
Yes.
Does this thought experiment offer a different perspective on the information paradox?
It does. It focuses on the idea that the information might be preserved within the entangled partner of the particle that fell into the black hole.
So instead of disappearing into the black hole or escaping through a wormhole, the information is mirrored in the particle that remains outside.
Exactly.
This is really intriguing. Can we dive into the details of this thought experiment?
Absolutely, but I think we should pause here.
Oh.
And pick up this discussion in our next segment.
Right.
It's a complex topic.
Yeah, this is definitely a deep dive that requires some time to digest. We've covered a lot of ground, from the basics of black holes and entanglement to the mind-boggling black hole information paradox and some of the proposed solutions.
Absolutely.
I'm already eager to hear more about this new thought experiment and what it might reveal about the fate of information in these cosmic mysteries.
It's going to be good.
I think so too.
All right.
That thought experiment you mentioned, the one about information being preserved in the entangled partner.
Yeah.
It's really piqued my curiosity. Can we unpack that a bit more?
Absolutely. So let's revisit the scenario.
Okay.
We have two entangled particles.
Right.
One falls into the black hole and the other remains outside.
Ew.
The thought experiment proposes that instead of being lost inside the black hole or escaping through a theoretical wormhole, the information of the particle that fell in is actually encoded within its entangled partner outside.
So it's like a backup copy of the information is stored in the particle that stayed behind.
That's a good way to visualize it. Even though the particle inside the black hole is beyond our ability to observe directly,
Right.
we can potentially learn about its fate by studying its entangled twin.
But how would we extract that information? What kind of measurements would reveal what happened to the particle inside the black hole?
Okay, so let's say our entangled particles are photons, and they're entangled in their polarization states,
Okay.
meaning the direction their light waves vibrate.
Right.
One photon has horizontal polarization and the other has vertical polarization.
Okay.
Because they're entangled, if we measure one and find it's horizontally polarized,
Right.
we instantly know the other must be vertically polarized.
That's like our coin flip analogy again.
Exactly.
One lands heads, the other must be tails.
Exactly.
But instead of coins, we're talking about the orientation of light waves.
Right.
Okay.
Now imagine the photon with vertical polarization falls into the black hole.
Okay.
We can't see it anymore, but we still have its entangled partner outside, the one with horizontal polarization. If we measure the polarization of this outside photon, we're essentially gaining indirect information about the photon that fell in.
So it's like using the outside photon as a mirror to reflect what happened to its twin inside the black hole.
That's a very good analogy.
Wow.
It's this concept of indirect measurement
Right.
that allows us to potentially access information that's otherwise inaccessible beyond the event horizon.
This is truly fascinating.
Yeah.
It's like entanglement creates a loophole in the black hole's information barrier.
Yeah.
But doesn't this raise questions about whether information is actually escaping the black hole?
Right.
It seems to contradict the idea that the event horizon is a point of no return.
You've hit on a crucial point. We're not saying the particle itself is escaping.
Right.
It's the information encoded within the entanglement that's potentially preserved.
Right.
Think of it like this. The information isn't traveling through space in the conventional sense. It's more like it's mirrored or reflected in the entangled partner outside the black hole.
I see. So it's not violating the laws of physics because the information isn't actually crossing the event horizon.
Right.
It's just being accessed indirectly through this spooky connection of entanglement.
That's the essence of it. And it's why some physicists believe that entanglement might be the key to solving the black hole information paradox.
It's like entanglement is a cosmic safety net, ensuring that information,
Yeah.
fundamental aspect of the universe,
Okay.
isn't truly lost.
Right.
But are there other properties besides polarization that could be used to test this idea?
Absolutely. Instead of photons and polarization, we could consider electrons and their spin,
Okay.
a quantum property that's like the particle's intrinsic angular momentum.
Okay.
Electrons can have either spin up or spin down.
So if one of these entangled electrons with spin up falls into the black hole, we could measure the spin of its partner outside the black hole to
Exactly.
figure out what happened to the one that fell in.
Exactly. If we find that the outside electron has spin down, we can infer that the one inside the black hole had spin up. It's another example of how entanglement can act as a tool for indirect measurement, helping us probe the mysteries of the black hole's interior.
This is incredibly thought-provoking. It's like we're using the language of the quantum world to decipher the secrets of black holes.
Yeah.
But I imagine there are also challenges to this idea. What are some of the obstacles that make this thought experiment so difficult to test in reality?
You're right. There are several hurdles to overcome.
Yeah.
One of the biggest is the issue of decoherence,
Okay.
a process that can disrupt entanglement.
Right.
Essentially, interactions with the environment can scramble or dilute the entanglement,
Right.
making it difficult to extract reliable information.
So the extreme environment inside a black hole with its intense gravity and Hawking radiation could potentially disrupt the entanglement.
Precisely. It's like trying to have a conversation in a noisy room.
Yeah.
If the background noise is too loud, the message gets lost.
Right. Another challenge, if I recall correctly, is the vast timescale involved.
Yes.
Even if entanglement survives inside a black hole,
Right.
the information wouldn't be released until the black hole completely evaporates,
Right.
which could take an unimaginable amount of time.
Yes, that's another major obstacle. We're
Yeah.
talking about timescales that dwarf the current age of the universe.
So even if we could somehow confirm that entanglement persists within a black hole, retrieving the information would be like waiting for a message in a bottle to wash ashore after billions of years.
Exactly.
But there's another question that comes to mind. Even if the information is eventually released, wouldn't it be incredibly scrambled and distorted by the black hole's chaotic environment?
That's an excellent point, and it leads to further questions.
Yeah.
Would the information still be readable after being subjected to the extreme conditions inside a black hole?
Right.
Would it be like receiving a letter that's been shredded and pieced back together where only fragments of the original message remain?
It seems like we're still in the early stages of unraveling this cosmic enigma.
Yeah, we are.
What are some of the most promising research directions that might help us answer these questions?
There are several avenues of exploration that hold promise.
Okay.
One is the development of a more complete theory of quantum gravity,
Right.
a theory that would unify the principles of quantum mechanics with general relativity.
That's the holy grail of physics, right?
Exactly.
A theory of everything
A theory of everything.
that can explain the universe from the smallest particles to the largest cosmic structures.
Exactly. And there are some intriguing candidates for such a theory, like string theory
Right.
and loop quantum gravity.
I've heard of string theory. It's the one where the universe is made up of tiny vibrating strings, right?
Yes.
Could string theory shed light on the information paradox?
It's definitely a possibility.
Okay.
String theory might provide a natural framework for understanding entanglement
Right.
and how it could play a role in preserving information within black holes.
So string theory could be the missing piece of the puzzle, connecting the dots between quantum mechanics,
Yeah.
gravity, and the fate of information.
It's a possibility worth exploring. Another exciting area is quantum information theory, which explores how information is processed and transmitted in the quantum realm.
So it's like understanding the language of the quantum world, how quantum systems communicate with each other.
Precisely.
Okay, could this help us understand how information might escape from a black hole?
Absolutely. Quantum information theory is already leading to breakthroughs in quantum computing and quantum communication.
Right.
And it could also offer new insights into the role of entanglement in preserving information within black holes.
It seems like entanglement is the common thread running through many of these potential solutions to the information paradox.
Yeah.
It's like this spooky connection between particles holds the key to understanding some of the deepest mysteries of the universe.
You're absolutely right. Entanglement is a fundamental aspect of quantum mechanics, and its implications are far-reaching. It might be the bridge that connects the microscopic world of quantum particles to the macroscopic world of black holes and the cosmos as a whole.
This has been an incredible deep dive. It's made me realize just how much we still don't know about the universe.
Yeah.
And how much there is left to explore.
It's exciting, though.
It is.
Even if we don't have all the answers to the black hole information paradox right now, the journey of trying to understand it is what's truly exciting.
Absolutely, and I think that's a perfect place to stop for today.
I agree.
It really feels like we've been on quite the journey,
Yeah, it has.
exploring the mysteries of black holes and grappling with the intricacies of entanglement and just pondering the fate of information in these cosmic enigmas.
Yeah.
It feels like every answer we uncover just leads to even more questions.
That's the beauty of scientific inquiry. It's a never-ending quest to expand our understanding of the universe. And the black hole information paradox is a prime example of how these explorations can challenge our fundamental assumptions about reality.
Yeah, it's definitely made me rethink everything I thought I knew about black holes and the nature of information itself. So where do we go from here? What are some of the next steps in trying to unravel this paradox?
One of the most exciting avenues is the pursuit of a unified theory of quantum gravity.
Right.
This would be a theory that seamlessly merges the principles of quantum mechanics with those of general relativity.
Ah, the elusive theory of everything. The holy grail of physics.
Exactly.
A theory that can explain the universe from the smallest subatomic particles to the largest cosmic structures.
Exactly. And there are some promising candidates for such a theory, such as string theory and loop quantum gravity.
Right.
These frameworks might hold the key to understanding how gravity behaves at the quantum level,
Right.
which could shed light on what happens to information inside black holes.
You mentioned string theory earlier.
Yes.
It's one where the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings.
Yeah.
How could string theory help us understand the information paradox?
So string theory proposes a higher dimensional reality than what we perceive.
Okay.
It suggests that these tiny strings vibrate in different ways,
Right.
giving rise to the various particles and forces we observe in the universe.
Right.
It's a very elegant and mathematically compelling framework.
So it's like the universe is a grand cosmic symphony, and the particles are different notes played on these vibrating strings.
That's a beautiful analogy. And what's particularly interesting is that string theory offers a natural way to incorporate entanglement. It could provide a mechanism for how information is encoded and preserved, even in the extreme conditions of a black hole.
That's fascinating. It's like string theory provides a bridge between the world of quantum mechanics and the world of gravity,
Yeah.
potentially resolving the conflict that lies at the heart of the information paradox.
It's certainly a path worth exploring.
Right.
Another promising area of research is quantum information theory. This field delves into the fundamental nature of information in the quantum realm. It explores how information is encoded, processed, and transmitted in quantum systems.
So it's like cracking the code of the quantum world, understanding how quantum systems communicate with each other. Could this help us understand how information might escape from a black hole?
Absolutely. Quantum information theory is already leading to breakthroughs in quantum computing and quantum communication. And it could also offer new insights into the role of entanglement in preserving information within black holes.
It seems like entanglement is the common thread running through many of these potential solutions to the information paradox.
It seems so.
It's like this spooky connection between particles holds the key to understanding some of the deepest mysteries of the universe.
You're absolutely right. Entanglement is a fundamental aspect of quantum mechanics, and its implications are far-reaching.
Right.
It might be the bridge that connects the microscopic world of quantum particles to the macroscopic world of black holes and the cosmos as a whole.
This has been an incredible deep dive. It's made me realize just how much we still don't know about the universe and how much there is left to explore. Even if we don't have all the answers to the black hole information paradox right now, the journey of trying to understand it is what's truly exciting.
Absolutely. And I think that's a great note to end on.
I agree. To all our listeners out there, keep questioning, keep exploring, and keep that sense of wonder alive.
Yes,
The universe is a vast and complex place.
it is.
And the more we learn, the more we realize how much more there is to discover. Who knows what groundbreaking discoveries await us in the future? Maybe one of you listening will be the one to finally unlock the secrets of black holes and the nature of information itself.
You never know.
Until next time, keep looking up at the stars and pondering those profound questions that they inspire.
Yes.
The journey of discovery is never truly over.
I love that